A-level further maths, differential equations, the integrating factor. Some first-order differential equations can be solved by the cleverness and spotting what you can do. The equation I have here looks awkward. We cannot use the separation of variables technique from A-level maths because of that awkward 1 and the combination of x and y in the 2yx term. However, if you look closely, you might find the little trick you can use to solve this. You might want to pause to think about it. The left-hand side is actually cunningly designed so that it is a complete differential. If you think back to when you're doing implicit differentiation, when you differentiate x squared y, you'll get first x squared dy by dx and then 2yx. So in fact, the left-hand side can be combined into a single differential. Once we've done that, we can integrate the right-hand side. We get x plus a constant, must remember the constant, and so we can make y the subject of our equation nice and easily. We end up with two terms, one of which does not have the constant in it, and one of which does. And when we look at second-order differential equations, we'll see something similar happening. So that differential equation we could solve using that clever little trick of the fact that it was a perfect differential on the left-hand side. However, most first-order differential equations are not of that form. Considering this equation, the left-hand side isn't the derivative of any function we know. So we have to have another technique. Now, the other technique we have is to find a factor such that we can turn our differential equation back into one which is exact. And this technique is called finding the integrating factor. So to solve an equation where we have dy by dx with coefficient 1 and then some function of x times y equals another function of x, then we first of all we need to integrate p of x. Once we've integrated p of x, then we take its exponent, and this is called the integrating factor. Okay, so it's e to the power the integral of p of x dx. Unlike other integrations, though, we do not want the plus c in this case. That would just add a constant multiple e to the power c throughout the equation when we use it, because what we do with the integrating factor is having multiplied it by this, we get an exact differential. It looks a bit awkward, and so it's much better to see what's actually going on with an example. So let's go back to that example we couldn't do and see what happens when we do it. Right, so first of all we look at this and we say, the coefficient of dy by dx is 1. That's good. We can go straight on to working out what p of x is. P of x is the coefficient of y. Then we integrate it. The integral of p of x, just integrating 1, is x plus a constant. But remember, we do not include that constant in what we do afterwards. So let's get rid of that. We're not going to actually use it. Okay, what we're going to do instead is we just carry on. We do work out our integrating factor. And since the integral of p of x is just x, the integrating factor is just e to the x. So we now multiply the whole equation by e to the x. And now we claim that that left-hand side is suddenly an exact differential. This integrating factor does the thing we wanted, and it does it by turning the handle, not by inspiration. All you need to do is apply the rule, and it will work. And in this particular case, our right-hand side is going to be nice and easy to integrate. You see, when we integrate, so we can integrate the right-hand side because it's just e to the 2x. Integral of e to the 2x, half e to the 2x plus c. This case, now, that plus c is really important It's part of our constant of integration of the whole equation. So when we finally integrate our whole equation, we divide across by e to the x. So e to the 2x over e to the x is just e to the x. And rather than dividing c by e to the x, we use the trick of multiplying it by e to the minus x. And so we get our solution. And so this integrating factor method can be applied to any first order differential equation of the right form. Okay, remember it has to be of the form dy by dx plus p of x times y equals q of x. All you do is integrate p of x, ignoring the plus c term. You multiply your whole differential equation by I of x, the integrating factor, and the left-hand side is magically a perfect differential. Having got that perfect differential, you now integrate your right-hand side. That's where it's going to be probably the most tricky bit. The example we had, I'd set it up so I of x times q of x was nice and easy, but you might well find that you got to do integration by parts or some such calculation. Having done that and remembering to include the plus c, you divide whatever you've got by I of x, and that is your answer. There'll be more examples of the integrating factor applied to cases in subsequent videos.